So yesterday we were discussing how to compute the median. Any questions, please, from the previous class? So I wrote down the questions, right? Yes. Questions. Yes. What is x naught for the discrete random variable case? Which value of x corresponds to x naught in the previous figure? Okay. Let me start recording. So good morning to everyone. Today what I have planned is to cover the computation of median value for discrete random variable followed by the conditional probability distribution function and conditional density function. Okay. Any questions from the previous class, please? So in the previous class, it has been asked how to compute the median value of a discrete random variable. Okay. So let me refer to the previous presentation for a yes. I have been referring to Bernoulli trial experiment, right? I will refer to the same experiment and I will try to explain you the method involved in computing the median of a discrete random variable. Okay. When I consider the Bernoulli trial experiment, that experiment involves only two possible outcomes. So consider an experiment. Today's date is 3rd, right? Okay. Am I right? Okay, right. Fine. Consider an experiment that has got only two outcomes. Two outcomes, right? So when I have only two outcomes, I call one outcome as desired outcome, the other one as undesired, not undesired. What we can say, other outcome I say. If the probability of occurrence of desired outcome is P, the probability of occurrence of the other outcome is 1 minus P. And further what I assume is the experiment is repeated n times. This is what the normal description is. When the experiment is repeated n times, any question please? Okay. When the experiment is repeated n times, okay, from the Bernoulli trial experiment, how did we show the probabilities? Okay. Probability of occurrence of the desired event, say 0 times. Okay. Probability of occurrence of the desired event, say 1 time. Okay. So what I consider from this experiment is I am assigning a random variable do the experiment. If you refer to Papalist's book, he will never use a random variable. He uses an random variable. The idea is RB stands for abbreviation. All abbreviations should be preceded by the article AN. That is the rule. Okay. So, and RV is assigned to the experiment. I call it as X. Okay. Now, what values the random variable takes? The values are indicated by small x. When I say random variable x is taking values, those values are represented by small x. So what values the random variable x can take? Small x, right? 0. What does it mean? The desired outcome is happening 0 times. Okay. Small x equal to 1. Desired outcome is happening 1 time. Desired outcome is happening 2 times. When the experiment is repeated, let me see the probability that the desired event is happening exactly n times. Now what I write is probabilities in the second row I will put. Probability of x taking a value of small x. What does it mean? How many times, what is the probability of getting the desired outcome exactly 0 times? What is the formula? NCK p power 0 1 minus p whole power n minus 0. That is one outcome. Probability, right, of the desired event happening 0 times. Next thing is the probability of the desired event happening exactly once. What is that probability? N 0. Okay. Why should I write k? NC0 for the first term. For the second, it is NC1 p power 1 1 minus p raised to n minus 1. Okay. The probability that the desired event happens exactly 2 times is NC2 p square 1 minus p n minus 2. This is what we have seen, right? Repeat this for so many events. When the experiment is repeated exactly n times, I want to know the probability that the desired event happens all the n times. This is what the problem. First row refers to the values taken by the random variable. The random variable under consideration represents how many times exactly the desired event is happening. Any questions till now, please? Okay. Then what is the distribution, cumulative distribution function for this? The cumulative distribution function is, how do I write? NC0, because this is the first event, n. Then when it comes to the case x takes a value of 1, what is the value of the distribution function? NC0 p power 0 1 minus p n plus n1 nc1 p raised to power 1 1 minus p raised to power n minus 1. When it comes to the case that the desired event is happening exactly 2 times, the value of the probability distribution function for n equal to, for small x equal to 2 is given by this expression. I hope I am clear in explaining the terms, putting down the steps, right? Any questions, please stop me. Okay. Like this, the cumulative distribution function continues. See, what is the last term? It includes all the values for small x. So how do I write that? Sigma nck p power k 1 minus p n power n minus k running from 0 to, what value shall I put, please? 0 to, one of you, please. No one is
N.
responding. What is?
0 to N.
Yeah. Yeah. Thank you. Right. Thank you. Now and then, please respond so that I also feel happy and get support from you, right? That is also important. I hope the three rows are clear. I have not written anything new. Only thing is I have placed the things in a different format, right? Now let us consider a typical case. So the typical case which I am going to discuss is being taken from the textbook. If you have your textbook before you, refer to page 65, wherein the Bernoulli trial experiment is discussed. For that, the values taken are n equal to 6. Probability of occurrence of the desired event is 0.25. Okay. So anyway, I am putting down those values. X, small x refers to value 0 because capital N is now 6. Number of times the experiment is repeated is 6. I should consider all 7 values. Out of 6 trials, the desired event is not at all happening. That is the case x equal to 0. Okay. Then what is the probability of occurrence of various repetitions of the desired event? For x equal to 0, I am taking those numericals straight away. Please, if you have the book, you can cross check. How do we get these numericals? By using the expressions which I discussed earlier. Okay. Yes. Little scroll it down. Okay. Yes. NC0 p power 0 1 minus p whole power n minus 0 is 0.1780. That is how I got the values. Then after 0.2966, I have 0.1318 if I am right. Next is 0.0330 0044 0002. Okay. Yes. Now the question is how to find out the median of this discrete random variable. Let us put down the values for the distribution function also. So this is 0.1780. That is the first value. Then the next value is I should consider sum of this value along with previous values. So 0.3560 plus 0.1780. So how much is it? 0.5340. The next entry for this row is 0.8306. Next entry for this row is 0.9624. So like this the values appear. 9998. When the last I missed one value, right? What could be 1753? Okay, 839624. Yes. Anyway, the last entry is 1. Before 1, I have this entry.
Sir, after 0.9624, it is
Yeah.
0.9954.
Yeah. 9954. I missed that. Thank you for pointing out. 9954 here. Okay. Here should be 54. Okay. Thank you. 9954. Okay. So, what the rule for computing the median now is, now we need to select a value x1, select, okay, a value x1 such that So where is the x1 values in this row? Select a value x1 in the first row of this table such that the distribution function value is less than or equal to 0.5, such that the distribution function value is less than or equal to 0.5. Okay, then select a value x2 such that distribution function value is just greater than 0.5. This is just less than or equal to, just less than or equal to. Okay, and in this case just greater than. Here this just is very important. This symbol says that. Why that just term is used? In this table, please let us refer to the first statement A, statement B. Select a value x1. Just let us start from minimum value of x to maximum value. The minimum value of x is 0. So the value of the distribution function, that means first row, third row I am referring to. Only first row, third row. When x takes a value of 0, distribution function value is 0.1780. Now let me consider the value of x equal to 1. That means third column I am referring to. When x equal to 1, the distribution function value is 0.53, which is greater than 0.5. So what value of x I should take? X equal to 0, I should take corresponding to x1, x1 equal to 0. Because when x equal to 1, the distribution function value has become more than 0.53. By definition, I need to select a value x1 such that fx of x1 is just less than or equal to 0.5. Okay, so x1 equal to 0. Apply the second B rule. Select a value x2 such that fx of x2 is just greater than 0.5. So when x takes a value of 1 in the table, okay, I am just moving the cursor. When x equal to 1, the distribution function value is just greater than 0.53. So x equal to 1, x2 equal to 1. Once we determine these two values, the median is computed using the formula median equal to average of these two values, x1 plus x2 whole divided by 2. So 0 plus 1 by 2. 0.5 is the median value for this discrete random variable. Any questions, please? This is what the yes. I hope n equal to 6 for yes. This is the example I am referring to. From this distribution function, when x equal to 0, the probability distribution function value is 0.1780. When x equal to 1, it has become 0.5340. So in this example, x1 is 0.1780, x2 is 0.5340. Take average of the two. The meaning of this value of median is, now median is 0.5. Okay. What it says, 50% the chance. Probability is also referred to as the chance. The chance that the random variable is less than or equal to 0.5 is 50%. When we consider a median of 0.5 and the probability that the random variable is greater than 0.5 is 50%. Is it fine? Any questions till now, please? Yesterday, someone has asked that question, this question, right? Is he online? The student who has asked this question in the previous class, are you able to unmute yourself?
Yes, sir.
Uh, what is your name?
Dheeraj, sir.
Uh, did you ask this? Did you ask question related to this in the previous class, please?
No, sir.
Here is someone has asked Madhu, I think, if I am right. Is it Mr. Madhu who has asked this question? How to find the um, median of a discrete random variable? Okay, okay, nice. If the concept is still unclear, please raise the question again. I will try to explain. Okay. Today, uh, after this, what I have planned to cover is the concept of conditional probability density function and distribution functions. Is there anyone having questions, please? In the previous topics, please unmute yourself and speak.
No, sir.
Thank you for the response. Who responded?
Riyaz.
Riyaz, right? Thank you for the response. So today, what I have planned is to cover the properties of conditional distribution and density functions. Okay. In the in one of the previous classes, we have seen what is the conditional probability. Okay. How did we define that conditional probability? We have considered a random experiment. We have considered the outcomes. We have defined events on that outcomes. So each outcome can be an event, or a group of outcomes together can be labeled as an event. So typically let A and B be the events defined on a random experiment. What does it mean? If I have sample space S, event A may be this, event B may be this. Okay, something of that kind. Or if I have a sample space, event A may be this, event B may be this, event C may be this. So this is what I mean by grouping of the outcomes to define events. Okay. What we have seen in one of the previous classes is if I have such events, I want to know what is the effect of the probability of occurrence of one event on the other. There is a formula for this conditional probability computation that is given by this. Okay, this already we have seen. Probability of A given B equal to probability of A intersection B divided by probability of B. Okay, now the logic is if I have probability for an event, okay, then there is probability distribution function, also probability density function. If that is the case, for the conditional probability also, probability of occurrence of event 1 given event 2, there should be conditional probability density function. Instead of B1, I will call event 1, 2. Okay. Similarly, there should be conditional density function for the conditional probability. Is it okay? It is logically satisfying argument, right? That is what we are going to discuss. So let me refer to the content of the text book. Okay. So what it says, properties of conditional distributions. So these are the properties of conditional distribution function. How many properties are listed? These 6 properties have been listed. Now just you try to see the argument. In the argument we have the conditioning event. When we defined conditional probability, what we said was the conditioning event should happen with a definite probability, and the probability of occurrence of that event should not be equal to 0. Okay, the reason is when I write probability of A given B as probability of A intersection B over probability of B, since the probability of occurrence of B is in the denominator, okay, so it should always be a non-zero value. For example, I may say probability of Mr. Or Miss X winning the election given she contests the elections. It is given by probability of A winning the election intersection A contesting in the election divided by A contesting in the elections. Okay, are you able to get probability of A winning given A contests? How do I get this probability? Probability that A wins as well as contests. Okay, I am writing something, okay, which is not clear. A winning given contests. Okay, yes, divided by this intersection, please, because 2 events should happen. This intersection divided by P contests. Suppose P, the probability of the person contesting contests 0, then this becomes undefined. It should never be 0. So that person should be very much there in the contesting candidates list. That is the importance of the definition, right? Then another example could be what is the probability of A being elected as a president given that A participates in the contesting process. Okay, so like that we can quote examples, right? Okay, let us come back to this textbook material where properties are listed out. When you see the argument for each function in all the 6 properties, okay, just you compare these properties with the properties of distribution function. What is the difference in the arguments? In the case of distribution functions, you did not have the conditioning event. Let us refer to property 1. In the distribution function, it is fx of minus infinity. Now it is fx of minus infinity given the event b. What is b? It is the conditioning event. So in the earlier discussion, what we told, fx of minus infinity is 0. What is the meaning of that? We are considering a value for the random variable x that is less than the smallest possible value that is taken by the variable. It is 0. So with conditioning event also, that is not getting affected. When it comes to second property, what is the meaning of fx of infinity given b? We are considering all values of the random variable in which case the conditioning event is not influencing the value of the distribution function. Okay. When it comes to third property, how third property is different from 1 and 2? Let us see the third property. What does it say? The conditional distribution function of x is bounded by 0 and 1. Okay, you take any value of the random variable. It is always between 0 and 1. And how is it third property different from first two properties? From the first two properties, I don't get the idea that the distribution function can never be greater than 1. But third property puts that point straight. Okay. So third property says under no circumstances the distribution function can take a value greater than 1 or less than 0. Is it fine? When it comes to fourth property, as you consider larger values for x, the values taken by the random variable, the distribution function is always an increasing function of x. That means as you include more and more values for the random variable, the distribution function will keep growing, or at least it remains there. Is it okay? It is a non-decreasing function of x. When it comes to fifth property, what is the fifth property? When random variable is lying in a range, the lower limit of the range is small x1, the higher limit is small x2. Okay, and when you see this argument of fifth property, actually there are two events. One is capital X is taking values less than or equal to x2, and capital X is taking values less than or equal to x1. Okay, when you combine these two disjoint events, what fifth property says is, if you consider the difference between the distribution function value at x2 and x1 is nothing but the probability that the distribution function random variable takes values in the range x1 to x2. So that property is not getting affected by the conditioning event. When it comes to sixth property, what it is conveying is the distribution function is continuous as you move from the right side of the variable. What does it mean? Fx of x superscript plus. Just you consider a value of x just above that, a delta increment on higher side. Whatever value the distribution function has got, same value the distribution function will have when you consider that exact value. So, okay, let me show one example so that the explanation becomes clear. Same Bernoulli trial experiment I will consider. It is far away. Okay, conditional. Okay, let me explain. Okay, so suppose I have a discrete random variable. X is taking values. Say x equal to 0, 1 value. Say 0.2. Then x equal to 1. Say 0.8. Okay. Then x equal to 3. This is 0.2. Okay. In this distribution function, what the sixth property says is, when you consider value 1, start at a value higher than 1, maybe here, 1 plus delta. What is the value of the distribution function? It is 0.8. The same value is applicable at x equal to 1 also. That is what we mean by 1 plus equal to fx of 1. It is 0.8. Then someone may argue, why fx of 1 should not be taken as 0.2. Okay, it is a logically valid question. To avoid such questions, by definition, the distribution function at a specific value of x will have a value equal to specific value plus delta. Okay? Value of the distribution function at specific value plus delta. So fx of 1 equal to fx of 1 plus delta. That is what the sixth property says. Here it becomes equal to 0.8. Any questions, please? If there are no questions, let me refer to the distribution function values, density function, right? How to go? Yes, okay. Once the distribution function, conditional distribution function properties are discussed, there should be the discussion on corresponding conditional density function. So you take the derivative of the conditional distribution function. We get the corresponding density function. See, what are the arguments in the density function? For this set of four properties, it is x given b. What is the conditioning event? Capital B is the conditioning event. The first property, let us see. Fx of x given b. It is greater than or equal to 0. It is a conditional density function is a non-negative. That is what it says. Can it take? Is there any limit on the maximum value taken by the conditional density function? There is no limit on the maximum value taken by the conditional density function. Is there? Can the density function take negative value? From property 1, it is clear that it can never take negative value. Is it clear? In the case of distribution function, the distribution function can never decrease. Hence, the derivative of this can never be negative. But the distribution function can remain at its previous value based on the experimental status continuously. That means the derivative of a constant is 0. Is it okay? Second property says area under the density function over all possible values of x, variable x. Perform integration of density function from least possible value of the variable to maximum possible value of the variable. If you take the area, that area equal to 1. So this is very important property in the context of you may be given an expression for a density function, something like e power minus x minus a whole square by b. Okay. Determine a so that fx of x is a valid density function, probability density function. So how do we go about? We will find out area under the density function, and from this we will compute a as a function of b and a. This is what it means, right? Second property is that whatever we discussed in the case of the probability density functions, same explanation holds good for the conditional probability density functions also. Okay. Let us see the third property. What the third property says? The third property says that when you when we take area under the density function between the least possible value for the random variable and a specific value for the random variable. What is the specific value? It is small x. I am referring to property 3. Okay. Okay, property 3. Yes. This small x is the upper limit for the integral. Okay. And what is the argument? It is the conditional density function. The independent variable is random variable. Values taken by that are xi. When you evaluate this integral, xi will disappear because xi is replaced by the limits minus infinity and small x. So upon substitution of limits, the resulting expression is a function of small x. Okay. So whenever you find area under the density function, right from minimum to maximum value, you will get area of 1. That is from property 2. If you find area under the density function from minus infinity to a specific value of the variable, you will get the value of the distribution function. That is property 3. Property 4 is, okay. What is property 4? I want to find the probability of random variable taking values in a range. Okay. Typically, we are given a Gaussian distribution function. I want to know what is the probability of Gaussian random variable taking values between x1 and x2. In that case, what I need to do? I need to compute area under the density function between those two values. This is what the area under the density function bounded by the values x1 to x2. So this is equal to probability that the random variable is lying between these two values. I hope the properties are clear. Any questions till now, please? I have just repeated whatever we discussed in the previous discussions, right? Here only conditioning event is an extra one, right? So see, next is example. This example is interesting. Okay, I wish to explain this. I hope you can read this text. Okay. What is the basic experiment? The basic experiment involves selecting a ball. There are 3 different colored balls. Okay. And there are 2 different boxes. Okay, box 1, box 2. There are 2 different boxes. In each box, there are different colored balls. So in each box, I have red colored balls, green colored, blue colored balls. Okay. Now the experiment involves selecting a particular color ball. So what are the steps involved? First step is I need to select the box. From that box, I need to select a particular ball randomly. Select a ball randomly. So there are 2 events. One is selecting a box. Second event is selecting a ball from that box. So the experiment involves selecting a box followed by selecting a ball. Now, selecting a box is represented by event B. Selecting a ball from that box is represented by another event. Now, I want to use a random variable to describe this experiment. What is the outcome of this experiment? It is finally the ball is being selected out. So I consider a random variable x, and I consider assigning values to the random variable x to represent the balls being selected. There are three different colored balls. So I will assign three numerical values to the random variable capital X. Is it okay? For example, capital X refers to a value of 1. Please refer to this table, first row. When random variable X takes a value of 1, it implies that the colored ball being selected out is red. Next is when the random variable takes a value 2, the experimental detail is green ball is being selected. The random variable x taking a value of 3 implies a blue ball is being selected. Then how to distinguish the uh, selection of box? Okay, there is little detail missing in this table. What I thought was, if the table had been like this, what is ball color? Box. If the table had been like this, I thought it would be nice. Just you also think, and whatever is convenient, please follow that. Okay. 1, 2, 3 are the values assigned to the random variable x. And what is the meaning of these values? The selected color is red, green, blue. Okay. Then as you move horizontally, here you will get 1. That means box 1. 2 means box 2. Okay. So how many light colored balls are there in each box? Those things are listed under column labeled 1. Labeled 1 means it is box 1. Labeled 2 means box 2. Okay, 80, 60, 10. Just you take sum of all the numericals. So when you consider the column labeled 1, when I add up all the numericals in that column, 5 plus 35 plus 60, total number of balls in box 1 I will get. Similarly, in column 2, when I sum up all the numericals, I get 150. That is total number of balls in box 2. Okay. Is it okay? Fine. Now, let me relate this concept to the conditional probabilities. Yes. Now, random variable x refers to the ball being selected. Now, you see the suppose I select ball box 1. From box 1, what is the probability of selecting a red ball? How many red balls are there in box 1? There are 5 red balls in box 1. Okay. So, when there are 5 red balls in box 1, probability of selecting red ball from box 1 is conditional probability. How is it represented? It is P of x equal to x1. Yes, I am placing the cursor around that. P of x equal to x equal to 1, given b equal to b1. Given b equal to b1 refers to box 1 is b selected. So what is that probability? 5 by 100. Okay. I will take 5 more minutes and I will close the session. Please have patience. Okay. In the same row, you have one more entry. Probability of selecting red ball when the selected box is B2. In selected box B2, how many red balls are there? 80. So 80 by 150. That is what we mean by conditional probability. So probability of selecting green ball, probability of selecting uh, blue ball. Okay. From each box are listed in this set of 3 rows. I hope the concept is okay. Now I got the conditional probabilities. These three rows, they have the conditional probabilities. Okay. Once conditional probabilities are there, I can always find out the conditional density function. How do I find out? It is a discrete random variable. So impulses will be there corresponding to x equal to 1, x equal to 2, x equal to 3. What is the strength of each impulse? The strength of each impulse is the probabilities associated with x equal to 1, x equal to 2, x equal to 3. What is the probability of x equal to 1? It is 5 by 100. So 5 by 100 times delta of x minus 1 plus 35 by 100 delta of x minus 2 plus 60 by 100 delta of x minus 3. If you see this equation, which just I have read out, I am trying to place the cursor, you will find that it is conditional probability density function. What is the conditioning event? B1 from box B1. That means there should be conditional density function fx of x given B2. When you consider conditioning event B2, what should be the constants associated with each impulse function? In place of 5 by 100, I should write 80 by 150. In place of 35 by 100, I should write 60 by 150. In place of 60 by 100, I should write 10 by 150. Is it okay? Once conditional density function is available, what is the corresponding conditional distribution function? How do I get? Just take the integration of that. So when you integrate delta function, you get step function. So wherever impulse is there, replace it by step. Wherever impulse is there, replace it by step function. That is how we get conditional distribution function. Is it fine? Now you see this P of x equal to 1. What is the probability of selecting red ball? So red ball will be selected from box 1 or box 2. What is the probability of selecting box 1 multiplied by probability of selecting red ball from box 1 plus probability of selecting box 2 multiplied by probability of selecting red ball from that box 2. Because these two are independent events, addition is shown. So probability of x equal to 1 is given in the textbook. Okay. Probability of x equal to 2, probability of x equal to 3. Now I got the probabilities. There is no conditioning event now. If there are no conditioning events associated with probabilities, the distribution and density functions that we write are also do not have the conditioning event. So fx of x is involving the impulse functions. Each impulse function is scaled by corresponding probabilities. 0.437 coming from p of x equal to 1. 0.39 coming from p of x equal to 2. 0.173 coming from x equal to 3. Once fx of x is available, density function, corresponding distribution function is given over here. Okay? They are plotted in this figure. Is it okay? Any questions still now? I hope. And the important observation to be made from this figure is the conditional distribution function is always less than or equal to the distribution function. When the conditional distribution function becomes equal to fx of x, when you see the figure, yes. So at this point both are equal. Okay. But at other values, the distribution function, which is shown by thick solid line, that is always on upper side compared to conditional distribution. Is another density function. This is what I have planned. Any questions? It is better if you respond. Kirti Kiran, any questions please? Amrita, Meet, Tanvi, Prakash.
No
Aditya.
questions, sir.
So I will stop at this point. And see, I need to upload one asynchronous class. Then what I thought is methods of defining conditioning event I will upload, probably with one problem. Okay. So from the same book, I will repeat. I will cover the topic. Then that would be followed by the discussion on the next chapter. Any feedback would you like to give on the way the content is being presented, or do you want some more examples to be considered? Any difficulty you are facing while preparing for the content? Because your minor is to be scheduled next week. So up to this topic, conditioning event, your minor will be there. And the next chapter to be discussed is this operations on one random variable. Let us have minor in the next week somewhere time. Okay, it doesn't matter even if you place it on Friday or Thursday next week, no problem. Okay. So if there are no questions, let me close the session. Thank you for staying with me. Okay, I'm closing the session. Varun is online.
Thank you, sir.
Varun, I'm closing the session. Is it okay?